Heaven help us all. One of my viewers here at Berkey Academy asked me a big favor, and he was going through a derivation from some notes that he found online about how to derive the Slutsky equation and couldn't follow all the steps. And let me just show you that document here real quickly. So it goes through a little graphical representation of the Slutsky idea, Slutsky equation idea, and then down here it starts a mathematical derivation. And this is not the kind of thing that I normally teach. It's the kind of thing that, yeah, I know, I've done it, but gosh, it's been a lot of years. So I'm going to do this. But in order to prepare everyone, because I want this to reach as large an audience as possible if you're interested in the Slutsky equation, this involves a lot of stuff. I mean, first it involves here setting up the Lagrangian equation, then it involves total differentiation here, and then it involves using Kramer's rule, and then a lot of simplifications, and finally down here we get to the Slutsky equation part. So I'm going to do this, but in this video what I'm going to do is just hit some preliminary things that we need to have in our mind before we try to go through this. So in particular, the three ingredients that you need to have in mind are how to set up a Lagrangian and take the derivatives for a kind of general case, general utility function. What is total differentiation all about? And then Kramer's rule and working with matrices and determinants and things like that. I'm going to go through these preliminaries in this video. In the next video, that's the one where I'm going to go through this handout step by step and show you where they're getting all these things that they're saying in this derivation, because it can be quite confusing if it's not all spelled out. I understand that. So if you don't need any reminders, just go ahead and skip to the next video. I'll put a link to that right here. And if you're a mere mortal like the rest of us, I'm going to go through now, starting with some of these things that we need to reload into our heads. I'm going to assume that my viewers of this video have seen this material before, but maybe you're a little rusty. You haven't seen it in a while, or you might have forgotten a few things, okay? So let's go ahead and get started here with these things we need to understand. Item number one, derivatives of the Lagrangian function for utility maximization. Now I've done this with an example functional form in another video. But here what we want to do is set up a general Lagrangian. And a general Lagrangian builds in two things. A utility function. And so let's have utility of, and instead of x and y, which I usually talk about, we're going to talk about good x1 and good x2 so that we can be consistent with this handout that we're going to be working through. And then we have a budget equation that we need to build in here. And so I usually use B for budget, but I'm going to change it to M for money. And so our budget equation would usually look something like this. So the price of x1 times the amount of x1 plus the price of x2 times the amount of x2 equals the amount of money we have. So what we want to do is set this up into a Lagrangian function. So in order to do that, we write usually L for the Lagrangian, and we take the utility function. We want to maximize the utility function of good x1 and good x2, and then we build in that budget constraint into one long equation with the lambda, the Lagrangian multiplier, m minus p x1 times x1 minus the price of x2 times x2. Okay? So there's our Lagrangian function. And whenever we go and we take derivatives, trying to maximize this, we're going to be taking three derivatives. We're going to be taking derivatives with respect to x1, x2, and lambda. Okay? So we're going to take the derivative of this Lagrangian function with respect to x1. We're going to take the derivative, let me scoot this up a little bit, of the Lagrangian function with respect to x2, and we're going to take the partial derivative of the Lagrangian function with respect to lambda. And what we're going to get out of these three derivatives is just going to be the derivative of the utility function with respect to x1 and x2 with respect to x1. I mean, there's not a whole lot more we can do with that except just write the fact that we're going to take the derivative. And then over here, since we have the x1 on this side, we're going to have lambda times minus p1 x1. When you take the derivative of that with respect to x1, it's just going to leave you minus lambda times the price of x1. And we're going to set that equal to 0. Very similarly here, derivative of utility with respect to x1 and x2 with respect to x2 minus lambda times the price of x2 equals 0, since we're trying to maximize utility here. Now the derivative with respect to lambda is just going to take into account this term right over here that has the lambda multiplied times it. And so what we're going to get is just the budget equation here. So it's going to be m minus the price of x1 times x1 minus the price of x2 times x2 equals 0. So this is what the three equations, and this is our first ingredient. This is the first thing we're going to see when we look at that derivation of the Slutsky equation. Okay, ingredient number 2. Ingredient number 2 is making sure we kind of remember the idea of total differentiation. So, total differentiation. Let me go back to blue color here. Make it a little bit easier to see. Total differentiation. Suppose we have an equation like this. Z equals, say, I don't know, x to the 5th. So we have two different explanatory variables on the right side, and we have a dependent variable on the left-hand side is the way to think about this. So x to the 5th plus, I don't know, say 7 times x times y plus 4 times y cubed. So we can see how each of these get treated a little bit differently. When we take the total derivative of this equation, what we want to do is see how every variable on the right, each explanatory variable, when there's a change, what are all the different ways that that can change the z, the dependent variable over here. So, whenever we do this, here's what we want to do. What we're trying to do is, instead of z, we're trying to see how z changes when any of these variables on the right-hand side are going to be changed. So instead of z over on this side, I'm sorry for my screen doing weird things when I set my hand on it, what we want is dz. The change in z, how z responds, can be written this way. Now what we want to do is go through and first take, here's the way I think of it, first take the derivative of everything here with respect to x. So here's an x to the 5th. The derivative of that is 5x to the 4th, and that's the rate at which z changes when x changes. But in order to put, remember these d's mean change, so in order to see how a change in x changes z, we append a little dx there. So when there's a change in dx, a very tiny change in dx, multiply that by that magnitude to see the magnitude of change in z. And then we want to take the derivative of the second term with respect to x, and that's going to be 7y, so plus 7y. Again, dx, because we're seeing how changes in x affect z. And there's nothing else with an x. So then we go back through and we take the derivative of everything with respect to y. So the second term has a y in it. So we have plus 7x, right? The derivative of this term with respect to y is 7x. But since we're seeing how changes in y affect z, we put a dy there. And then we have one last term that only involves y, so we're going to say plus, take the derivative of that with respect to y, that's going to be 3 times 4 is 12, y squared dy, because we want to know how when we change y, how does it change x? Well, we're going to have to multiply that change in y by this magnitude and by this magnitude, the 7x and the 12y squared. So this would be called the total derivative, or the total differential, some people will call it. And then we could group if we wanted to, right? We could group the things with the dx together. We could group the things with the dy together. But this is basically the idea. So we're going to see that in our Slutsky derivation. The third thing, and we're going to spend more time on this, is Kramer's rule and matrices. So what in the world is Kramer's rule? Let's go through a quick example of how you can use Kramer's rule so that when we get into our Slutsky derivation, we won't have any problems. So 3, Kramer's rule. Now you probably, since you've studied Kramer's rule, you know that Kramer's rule has something to do with solving systems of linear equations. So let me give us a system of linear equations to work with here. We'll use x, y, and z. And so let's say 2x plus 1y. And I'm writing the 1y on purpose so that we can visualize what's going to happen to that 1, plus 3z equals 3. That's our first equation. We're going to have 3 equations and 3 unknowns here. 1x minus 1y minus 1z equals, let's say, 0. Make that look more like a z. And let's make our third equation something 3x plus 2y plus 1z equals, and let's say 0 again. That'll make our life a little bit easier when we're solving these. Now, in matrix algebra terms, there are several ways you can solve this. You could just do it kind of by hand, right? It's only 3 equations and 3 unknowns. That wouldn't kill you. But in linear algebra, when you get lots of equations and lots of unknowns, there are some ways that you can simplify this. For example, we could define a matrix, let's call it D. I'm going to call it capital D. Matrix capital D. We could rewrite this series of equations. Let me say how you usually might see this in a textbook. We could rewrite this way. A is a matrix times x. Well, x is going to be our various variables here, x, y, and z actually. Ax equals little d. A lot of times you'll see this set up in a linear algebra book this way. I'm going to change our notation slightly just to help us match what they do in this derivation we're going to do in the next video, and I'm going to call this d times x, where x is actually representing all these explanatory variables, x, y, and z, equals, I'll just call it little a. What does this mean? Well, it means that we can write in matrix form the coefficients that multiply times x, y, and z. So we just write them down. Over here is the 2, 1, and 3. Those all multiply times x, so 2, 1, and 3. Here's a 1 minus 1 and 2, so 1 minus 1 and 2, and a 3 minus 1 and 1, 3 minus 1 and 1. And we could write x, y, and z as a vector. And that's going to equal all the three things that these three equations and three unknowns equal on the right. So 3, 0, and 0. Okay? Now let me actually do that 3, 0, and 0 in a different color, because that's going to help us see what's going on. 3, 0, and 0. Okay? What Kramer's rule says is, one way you can solve this system of equations is by two determinants. Two determinants. And here are the two determinants. You want to take this vector of 3, 0, 0, and suppose we want to just solve for x, right? We just want to solve for x. Then we can solve for x this way. X is going to be equal to, we make a determinant, and the determinant we want to set up, what we want to do is take this vector and replace these values that are the coefficients for x, replace those with the 3, 0, 0. So we take the 3, 0, 0, 3, 0, 0, and then we keep these other values in this matrix the same. So 1 minus 1, 2, 1 minus 1, 2, 3 minus 1, 1. And we take that determinant on the top of a fraction, and then on the bottom of the fraction we need another determinant. And the determinant that goes on the bottom of the fraction is just our original matrix of coefficients over here. So 2, 1, 3, 2, 1, 3, 1 minus 1, 2, 3 minus 1, 1. Okay? And so we could call, again, this is to get you thinking in terms of some of the notation we're going to see in the Slutsky equation derivation here, is, remember, this matrix right here, this is what we're calling D, right? That's D. And so what we have on the bottom here is the determinant of D. What we have here on in the numerator is, part of it is the determinant of D, but part of it isn't. Part of it is the set of what these equations are equal to, 3, 0, and 0. Now let's go through and do this by hand. So again, this is a way of reminding ourselves of how this actually works. It's going to make things flow a lot more easily in the next lecture. So let's go ahead and let's find this determinant on top. Now there are a lot of ways that you can find a determinant. There are at least 3 different ways that I've been taught how to do this. Let's just write out the way that we're going to use. What we're going to do is we're going to take each of these red numbers, the 3, the 0, and the 0, and we're going to multiply them times the cofactor. So we're going to take each red number and we're going to multiply those times the cofactor. Now the cofactor, let me just write that up here, cofactor. The cofactor is a signed minor. Yes, I know there's a lot of language here. Here's the basic idea of what a cofactor is. The cofactor is, let's just go ahead and do it. This will make it actually easier. So the 3, let's go ahead and write down here what the top is going to be. We take the 3, and then we need to multiply that times a determinant. And that determinant is what we call a minor. Minor. And this minor is what we're going to get if we take this top determinant that we're working on right here, and since 3 is in the first row and in the first column, we're going to cross out the top row. We're going to cross out the first column. And the minor that we're interested in are these numbers that are left. The numbers that are left, the -1, -1, 2, and 1. So let's go ahead and write those down. -1, -1, 2, and 1. That's what's called the minor of the element 3. Another way that we could represent this minor is, since the number 3 is in the first row and the first column, then whatever we're going to call this, right, whatever we're going to call this matrix here, well, actually we can do it this way. Since we have the same minor down here in -1, -1, 2, and 1, right, that we were just writing down here, we could call this minor by this name, D. So it's the matrix D, 1, 1. D11 means it's the minor, but crossing out the first row and the first column, right? Crossing out the first row and the first column. But one other thing we have to do to this minor in order to get what we would normally call this cofactor here. The cofactor is a minor that has the proper sign on it. Now, if it's been a while since you've done determinants of 3x3 matrices, or if you haven't seen it done this way, what you have to do is take the element 3, multiply it by the determinant of the minor, but then you have to adjust the sign of the minor. And here's how you do it. Let me get another color here. You multiply what you're going to get here by -1 raised to the I plus j. I know, information overload. Information overload. So really, the complete story here is the first thing we're going to do, it gets easier, I promise, is we're going to take 3 times -1 to the I plus j, and I is what row the number's in, j is the column. So in this case, I is 1, j is 1. So what we're going to do is we're just going to square the -1, and that -1 will just become the number 1. No big deal here. This minor, along with this -1 to the I plus j, that is what we call a cofactor. Cofactor. So in order to find the determinant of a 3x3, just to summarize here, you take each element, and what we're going to do, you could use the first row, we're going to use the first column. Take each element of the first column and multiply it by its cofactor, which is a signed minor. All right. Now that we've got that out of the way, things are going to flow much more easily. So 3 times that plus 0 times, now we need -1 to the I plus j. Now this 0 is in the second row, first column. So that's to the 2 plus 1. That's going to be an odd power, 3. So that sign is going to matter here. It's not really going to matter because we're multiplying it all by 0. Right? But let's set it up anyway. What's the minor going to be for this element, this 0? Well, again, we cross out. See if I can get rid of that yellow without messing everything else up. The minor is going to be what we get if we cross out that row and that column. So what we want is the 1 and the 3, and the 2 and the 1. And then the next term is going to be plus. All right, so we're moving down here to this 0. We cross out that row and that column, and we're going to have 0 times -1 raised to the I plus j. That's the third row and the first column. So that's raised to the 4th power. 3 plus 1. So that's going to be just 1. That's not going to matter now. It's not going to matter anyway because we're multiplying everything by 0. But here's the minor. The minor up here is the 1, the 3, the -1, and the -1. So 1, 3, -1, -1. Now, the last thing we need to remind ourselves of, if it's been a while and we're rusty on finding determinants, is how do you find a determinant of a 2 by 2? To find a determinant of a 2 by 2, you multiply these diagonal elements. So it's going to be minus 1 times 1. So let's go ahead and set that up. We take this 3 times positive 1, so it's going to be 3 times positive 1 times minus 1 times 1. It's minus 1. And then we subtract these off diagonal elements here. These, I guess, the other diagonal. Subtract 2 times minus 1. So minus 2 times minus 1, which is going to be minus a minus 2, right? Minus a minus 2, which is going to be plus 2. Okay? And then plus 0 times 1 cubed. Well, that would be 0 times, minus 1 cubed. It would be minus 1 times, and then we would do in brackets 1 times 1 minus 2 times 3, right? Now this whole section is going to go away because of that 0. Then lastly, this one is also going to go away, but let's just do it quickly anyway in case there's somebody rusty. Now if you know all this and you want to go ahead and skip to the next video, go ahead. You won't hurt my feelings. So plus 0 times minus 1 to the 4th power, well that's just going to be 1, times, in brackets, 1 times minus 1, well that's minus 1, minus 1 times 3. So it's minus a minus 3, which is going to be a plus 3. Alright, so trying to wrap all this up, we have 3 times, this is just 1, okay, so 3 plus, well, that's all going to be 0, plus that's all going to be 0, okay? So what we've done there is just find the determinant of the top. Find the determinant of this top thing. And we're solving for x again. And that's why we replaced that first row, the x row, with these values. So we got 3. That's the numerator. Now we need to find the determinant of the bottom thing, this thing we're calling D. Let's do that real quickly. Let's make this a little smaller. Let's slide it over and make it a little smaller. So let's tackle this bottom part and find that determinant. And I'll go much more quickly here so you don't get bored. So that determinant is going to be 2 times, and then here is the minor, well 2 times minus 1 raised to the I plus j, that's 1 plus 1, so that's just squared, times the determinant of the minor here. So minus 1 to 1, because we're going to cross out the top row in the first column, plus 1 times minus 1 raised to the I plus j. I, second row, first column, 3, times the determinant of, so we cross out the second row, we cross out the first column, and what's left? 1, 3, 2, 1. 1, 3, 2, 1. Try to erase those red lines. And now we deal with the 3. Plus 3 times minus 1 to the I plus j. I is the third row. J is the first column, so to the 4th, times the determinant of what's left when you cross out that row and that column. 1, 3, minus 1, minus 1. Okay. So now we're trying to just figure out what goes on the bottom of this equation whenever we want to solve for the value of x in this series of 3 equations and 3 unknowns. We're almost there, guys. So here we have 2 times 1, 2 times 1 times minus 1 minus 2. So that's plus 2. plus 1 times minus 1 times minus 1 times, in brackets, 1 minus 6 plus 3 times minus 1 to the fourth is just 1 times minus 1 minus 1 times 3 is a minus 3. Okay, so we've got plus 3. So what are we ending up with here? 2 times 1 plus minus 1 times 1 minus 6 is minus 5, so that's plus 5, plus 3 times minus 1 plus 3 is positive 2 times 3. So 3 times 2 is 6. So 2 plus 5 plus 6 equals 13. So all that work has told us that the bottom, the determinant down here on the bottom, is 13. So that tells us that x equals 3/13. So that equals x. I know that was a lot of work, and I know that was painful, but trust me, keep this fresh in your mind when you watch the next video. We're going to start off with these 3 equations. We're going to do some total differentiation, and then we're going to use Kramer's rule, and we're also going to be on the fly doing some determinants here. And we're going to be also talking about minors and cofactors a little bit, okay? So, keep all of this in mind, where in the next video we're going to delve into the Slutsky equation derivation. See you then.